Two tiny particles can be connected across the entire universe. Touch one, and the other instantly reacts, no matter how far apart they are. This sounds completely impossible. Nothing travels faster than light. Tonight we're discovering how scientists prove this impossible connection is real, and how it's powering the most advanced technologies on Earth. Before we dive into this quantum mystery, drop a comment about where you're listening from. If you enjoy these explorations of impossible physics, consider subscribing. These journeys into the deepest mysteries are meant to be shared. Einstein thought he'd caught scientists making a huge mistake. He designed what seemed like the perfect thought experiment. Two particles meet briefly, then fly apart forever. Scientists claimed something impossible would happen next. Measuring one particle would instantly change the other particle, even if they were on opposite sides of the universe. Einstein called this ridiculous. He coined a phrase dripping with scientific mockery: spooky action at a distance. Nothing could influence anything else faster than light speed. He worked with two colleagues to create an elegant trap. They called it the EPR paradox, named after their three last names. Einstein was certain this would destroy the theory once and for all. The universe had other plans. Einstein's thought experiment didn't destroy anything. Instead, it accidentally predicted one of nature's most extraordinary phenomena. The greatest physicist of all time had discovered something he refused to believe. When scientists create these connected particles, something magical happens. The particles become what we call quantum twins. They share a single, invisible connection that defies every rule of normal physics. Picture two coins that always land opposite each other. When one shows heads, the other always shows tails, no matter how far apart you flip them, no matter how fast you separate them. Real quantum twins work exactly like these impossible coins. Scientists call this connection entanglement. The particles get tangled together in a way that never breaks. The moment you check one particle's properties, its distant partner snaps into the opposite state. Thousands of experiments have tested this connection. The relationship never fails. When one particle spins one direction, its twin always spins the opposite direction. Before you check either particle, both exist in a ghostly state. They hold all possible properties at the same time. Scientists call this superposition, being in multiple states simultaneously. The instant you measure one, both particles choose definite, opposite properties. This connection operates faster than anything should be able to move. Light takes time to travel between distant objects. Information takes time to cross space. But entangled particles ignore these fundamental speed limits completely. Scientists discovered something that seemed to violate Einstein's most famous rule. Nothing travels faster than light. This principle forms the foundation of modern physics. Yet quantum twins communicate instantly across any distance. When you measure one particle in New York, its partner in Tokyo reacts immediately. Not in a few milliseconds. Not after light could travel between them. Instantly. As if distance means nothing. This creates what physicists call the locality problem. Objects should only influence things in their immediate neighborhood. But quantum entanglement seems to ignore space entirely. The connection operates as if the universe has no size at all. Einstein spent the rest of his life trying to explain this away. He insisted hidden variables must secretly coordinate the particle's behavior. Reality had to make sense. The universe couldn't really operate through impossible connections. Another brilliant physicist watched Einstein struggle with growing fascination. Erwin Schrödinger saw something Einstein missed completely. This wasn't a flaw in the theory. This was nature's deepest secret revealing itself. Schrödinger gave this phenomenon its official name in 1935. He called it entanglement, a word that perfectly captured how particles could become inseparably tangled together. The name stuck immediately. Unlike Einstein, Schrödinger embraced the strangeness. He recognized entanglement as quantum mechanics' most fundamental feature. Two particles could share a single quantum identity that transcended space and time. The physics community gradually accepted what Einstein rejected. Entanglement wasn't a bug in the theory. It was the feature that made quantum mechanics unique. It revealed that reality operates through connections invisible to human experience. Schrödinger's naming marked a turning point in physics. Scientists stopped trying to explain entanglement away. They started asking how to use it instead. Entangled particles operate as parts of a single, distributed object. Space cannot break their connection. Time cannot weaken their coordination. They remain unified despite appearing completely separate. Scientists call this non-locality, the technical term for when objects act as one despite being many places at once. This violates our deepest intuition about how the world works. Things should be where they are, not everywhere at once. Yet quantum experiments prove non-locality operates throughout nature. Particles routinely transcend the boundaries of space. They maintain perfect coordination across distances that dwarf human comprehension. This creates what physicists describe as a single, undivided quantum system. The two particles aren't really separate. They're different pieces of the same invisible whole. Measuring either piece instantly affects the entire system. Non-locality forces us to rethink the nature of space itself. Distance becomes a kind of illusion when quantum connections are involved. The universe operates through deeper connections than our senses can detect. The act of measurement performs a kind of magic on entangled particles. Before observation, both particles exist in a state of perfect uncertainty. The moment someone checks either particle, the entire quantum system snaps into definite reality. Scientists describe this as wave function collapse, the process where ghostly possibilities become concrete facts. The invisible mathematical object that connects both particles suddenly chooses specific properties for each twin. This collapse happens simultaneously at both locations. No signal travels between the particles. No force pushes them into coordination. The collapse simply occurs everywhere the quantum system exists, all at once. The timing of this collapse violates every classical understanding of cause and effect. In normal physics, causes precede effects, and influences take time to travel. Quantum collapse operates outside these rules entirely. What triggers the collapse remains one of physics' deepest mysteries. The measurement itself seems to force reality into existence. Before observation, the particles exist in a realm of pure potential. After measurement, they become part of our concrete world. Entangled particles display a coordination more precise than anything else in nature. When one particle's spin points up, its partner always points down. When one shows vertical polarization, the other always shows horizontal. The correlation reaches mathematical perfection. Scientists have tested millions of particle pairs. The relationship never breaks down. No exceptions. No partial correlations. Either particles are perfectly entangled or they're not entangled at all. This perfection extends to every property the particles possess. Spin, polarization, momentum, energy. Whatever you measure on one particle, its partner displays the exact opposite. The coordination covers every aspect of their quantum existence. The precision of this correlation exceeds anything classical physics can explain. Classical objects might synchronize their behavior, but quantum twins share their identity. They don't coordinate. They are coordination itself. This perfect relationship forms the foundation for all quantum technologies. Scientists have learned to exploit this flawless correlation to create unbreakable codes, ultra-precise sensors, and revolutionary computers. Entanglement destroys one of physics' most fundamental assumptions. Classical physics assumes objects have definite properties whether you observe them or not. A spinning ball rotates in a specific direction even when no one watches. Quantum entanglement proves this assumption wrong. Particles don't possess definite properties before measurement. They exist in a state physicists call indefinite reality, having the potential for all possible properties simultaneously. This insight undermines what philosophers call local realism, the belief that objects are what they appear to be, located where they appear to be. Quantum particles are neither fully real nor fully local until observation forces them to choose. The implications extend beyond physics into philosophy itself. If fundamental particles don't possess definite properties, what does this mean for the nature of reality? Are we creating the world through the act of observation? Einstein never accepted this interpretation. He insisted the moon is there whether or not anyone looks at it. But quantum experiments suggest Einstein was wrong. The quantum moon exists in all possible locations until someone bothers to check. Individual quantum measurements produce completely random results. You cannot predict whether any single particle will spin up or down. Each measurement is like flipping a perfect coin, genuinely unpredictable. But the correlations between entangled particles follow rigid mathematical laws. While each particle's behavior is random, their relationship is absolutely determined. Chaos at the individual level creates perfect order at the system level. This combination of randomness and correlation creates a unique signature. No classical process can reproduce this pattern. Random events that follow classical physics produce different statistical relationships entirely. Scientists exploit this signature to prove entanglement is real. They measure thousands of particle pairs and analyze the statistical patterns. Classical correlations always fall short of the quantum theoretical predictions. This quantum randomness serves a deeper purpose in nature. It prevents any mechanism from secretly coordinating the particle's behavior. True randomness ensures the correlation emerges from genuine quantum entanglement, not hidden classical causes. Einstein proposed his thought experiment in 1935. Scientists couldn't test it for decades. The technology needed to create entangled particles simply didn't exist.
6.
Quantum theory made precise predictions about what experiments would find. But predictions aren't proof. Scientists needed to actually create entangled particles and measure their impossible correlations. The first crude experiments began in the 1970s. These early tests suffered from technical limitations that left room for doubt. Skeptics could still argue that classical physics might explain the results. Gradually, experimental techniques improved. Scientists developed better ways to create entangled particles. They built more sensitive detectors. They closed the loopholes that allowed classical explanations. By the early 2000s, the experimental evidence became overwhelming. Multiple independent laboratories confirmed entanglement's reality. What began as Einstein's thought experiment had become established scientific fact. Today's scientists don't just study entanglement. They use it to build impossible devices. Quantum computers harness entanglement to solve problems classical computers never could. They process information in ways that transcend normal computational limits. Quantum cryptography uses entanglement to create unbreakable codes. Any attempt to intercept quantum encrypted messages automatically destroys the information. The laws of physics themselves protect the communication. Scientists are building quantum sensors that exploit entanglement to measure things with unprecedented precision. These devices detect gravitational waves, map magnetic fields, and time atomic processes with accuracy that redefines measurement itself. The quantum internet is emerging from research laboratories. Networks of entangled particles will soon connect quantum computers across continents. Information will flow through quantum channels that operate outside classical space and time. What Einstein called spooky action at a distance has become the foundation of a technological revolution. The impossible connection between quantum twins is transforming how we compute, communicate, and understand the deepest nature of reality itself. Particles don't exist the way you think they do. Instead of being in one place with definite properties, they exist as mathematical possibilities. Scientists describe this ghostly existence with something called a wave function. The wave function is like a mathematical recipe that contains every possible state a particle could have: where it might be found, what speed it might have, which direction it might spin. All possibilities exist simultaneously in this invisible mathematical object. Think of it as nature's probability map. The wave function spreads across all locations where the particle might appear. It assigns different chances to different outcomes. The mathematics tells you where you're most likely to find the particle, but never where it actually is. This mathematical description revolutionized physics completely. Instead of tracking particles like tiny billiard balls, scientists learned to calculate probabilities. The wave function became the fundamental tool for describing quantum reality. Before quantum mechanics, mathematics described what objects were doing. Now mathematics describes what objects might do. The wave function captures this realm of pure potential that exists before measurement forces reality to choose. Quantum particles can be in multiple contradictory states simultaneously. Scientists call this superposition, the ability to exist in all possible conditions at the same time. This violates every intuition about how objects should behave. An electron can spin both up and down simultaneously. A photon can be vertically and horizontally polarized at the same time. A particle can exist at multiple locations simultaneously. These aren't approximations or shortcuts. They're literal descriptions of quantum reality. Superposition isn't like being unsure about something. It's not that we don't know which state the particle is in. The particle genuinely exists in all states simultaneously until something forces it to choose. This creates what physicists describe as quantum parallelism. While classical objects must choose one state or another, quantum particles explore all possibilities at once. They exist in a realm of infinite potential that collapses only when observed. Superposition makes quantum mechanics fundamentally different from classical physics. Objects don't just have properties. They have the potential for all possible properties simultaneously. Nothing in quantum mechanics is more puzzling than what happens during measurement. The instant you observe a quantum particle, something dramatic occurs. All the particle's ghostly possibilities collapse into one definite reality. Scientists call this the measurement problem because no one fully understands how it works. Before observation, the particle exists in superposition, all states at once. The moment someone checks, the wave function collapses. the particle suddenly has definite properties. This collapse happens instantaneously across the entire quantum system. If a particle was spread across a room in superposition, the measurement instantly localizes it to one specific spot. The collapse doesn't travel. It simply occurs everywhere simultaneously. The act of observation seems to create reality itself. Before measurement, particles exist in a realm of pure possibility. After measurement, they become part of our concrete, definite world. The boundary between potential and actual reality gets crossed in that instant. What triggers this collapse remains one of physics' greatest mysteries. The measurement apparatus somehow forces the quantum world to choose definite properties from its infinite menu of possibilities. You cannot know everything about a quantum particle simultaneously. This isn't due to imperfect instruments or measurement techniques. It's a fundamental law of nature called the uncertainty principle. The more precisely you measure a particle's position, the less precisely you can know its speed. The more accurately you determine its energy, the less accurately you can measure the time. These pairs of properties are called conjugate variables. Knowing one precisely makes the other completely uncertain. Werner Heisenberg discovered this principle and realized it wasn't a limitation of measurement tools. It's built into the fabric of reality itself. Nature prevents perfect knowledge about quantum particles as a matter of fundamental law. This uncertainty emerges from wave-particle duality. Particles behave like waves, and waves naturally spread out in space and time. The more you try to pin down where a wave is, the more unclear its wavelength becomes. The uncertainty principle sets absolute limits on measurement precision that no technology can overcome. It's not a challenge to be solved. It's the way quantum reality operates at its deepest level. Classical physics promised complete predictability. If you knew a particle's exact position and speed, you could predict its future perfectly. Quantum mechanics shattered this dream forever. The wave function doesn't tell you what will happen to a particle. It tells you the probability of different outcomes. You can calculate the chances of finding an electron in different locations, but you can never predict exactly where it will appear. The wave function square gives you these probabilities directly. Where the wave function is large, you're likely to find the particle. Where it's small, the chances drop dramatically. Where it's zero, the particle will never appear. This represents a fundamental shift from certainty to probability. Classical physics dealt with definite trajectories and predictable outcomes. Quantum physics deals with probability clouds and statistical predictions. Even perfect knowledge of the wave function only gives you probabilities, never certainties. This isn't a temporary limitation. It's how quantum reality actually works at the deepest level. Electrons don't orbit atomic nuclei like planets orbit the sun. This familiar picture is completely wrong. Instead, electrons exist as probability clouds that surround the nucleus in complex, three-dimensional shapes. These probability clouds show where electrons are most likely to be found. Some regions have high electron density. The electron spends lots of time there. Other regions have low density or are completely forbidden. The shapes of these clouds depend on the electron's energy level and angular momentum. Some clouds are spherical. Others look like dumbbells or more complex geometries. Each shape represents a different quantum state the electron can occupy. Unlike planetary orbits, these probability clouds don't represent motion paths. They represent the electron's quantum presence distributed throughout space. The electron doesn't move around the nucleus. It exists as a standing wave pattern. This quantum model explains atomic behavior far better than planetary orbits ever could. It predicts chemical bonding, atomic spectra, and electronic properties with remarkable precision. Electrons possess a property called spin that has nothing to do with actual rotation. Quantum spin is an intrinsic property like mass or electric charge. It's one of the universe's most fundamental features. Unlike classical spinning objects, quantum spin can only have specific values. For electrons, spin comes in exactly two varieties, spin up and spin down. There are no intermediate values, no gradual changes, just two discrete possibilities. Before measurement, an electron exists in a superposition of both spin states simultaneously. It spins up and down at the same time. The moment you measure the spin, the electron suddenly chooses one definite direction. Scientists discovered spin by accident while studying atomic spectra. Certain spectral lines split into pairs when atoms were placed in magnetic fields. This splitting revealed that electrons carried an additional quantum property. Spin plays a crucial role in determining matter's properties. It governs how electrons fill atomic orbitals. It determines which atoms can form chemical bonds. It's responsible for magnetism in materials. Photons, particles of light, they have their own version of quantum weirdness. Instead of spin, photons have polarization. Like electron spin, photon polarization can exist in superposition until measured. A single photon can be vertically and horizontally polarized simultaneously. It can vibrate in all directions at once until something forces it to choose a definite orientation. This creates the same mysterious behavior that electrons display with spin. Polarizing filters act like measurement devices for photons. When polarized light encounters a filter, each photon must choose whether to pass through or get blocked. The filter forces the superposition to collapse into a definite state. Scientists use polarized photons to study quantum mechanics because they're easier to manipulate than electrons. Photon polarization experiments revealed many of quantum theory's strangest predictions. The parallel between electron spin and photon polarization shows that quantum weirdness operates across all types of particles. Different particles may have different properties, but they all follow the same bizarre quantum rules. Quantum particles behave like waves under certain conditions. This wave behavior creates interference patterns, regions where waves strengthen each other and regions where they cancel out completely. In the famous double-slit experiment, individual particles create interference patterns just like waves do. Each particle somehow goes through both slits simultaneously and interferes with itself. This proves that single particles exist in superposition. The interference patterns disappear the moment you try to determine which slit each particle goes through. The act of measurement destroys the wave behavior. Particles suddenly start behaving like classical objects with definite paths. Quantum interference allows particles to reach some locations and completely avoid others. The probability waves that describe particle behavior can reinforce or cancel each other, creating forbidden and enhanced regions. This wave-particle duality lies at the heart of quantum mechanics. Particles aren't just particles, and waves aren't just waves. Quantum objects are something entirely different that can display both characteristics depending on how you observe them. Quantum weirdness disappears when particles interact with their environment. This process is called decoherence, the destruction of quantum superposition through environmental interference. Real particles are never perfectly isolated. They constantly bump into air molecules, absorb stray photons, and interact with electromagnetic fields. Each interaction acts like a tiny measurement that partially collapses the wave function. Large objects contain trillions of particles, each interacting with the environment billions of times per second. This creates so much decoherence that quantum superposition becomes impossible to maintain. Classical behavior emerges from quantum foundations. Decoherence explains why quantum effects become invisible at macroscopic scales. It's not that large objects don't follow quantum mechanics. They do. But environmental interactions destroy the quantum coherence so quickly that only classical behavior survives. Scientists must work extremely hard to isolate quantum systems from their environment. They use vacuum chambers, ultra-low temperatures, and electromagnetic shielding to preserve quantum coherence long enough to study it. How do you create two particles that share a single quantum soul? Start with one particle that has no spin at all. Then watch what happens when it breaks apart. Scientists call this process particle decay. A single particle with zero spin suddenly splits into two separate particles. Each new particle carries spin, but they must balance each other perfectly. If one spins up, the other must spin down. This splitting event creates instant entanglement. The two new particles share the original particle's quantum state. They become quantum twins the moment they're born from their parent particle. The conservation laws of physics force this connection. The original particle had zero total spin. The two daughter particles must maintain that zero total. They become locked in perfect opposition forever. Particle decay transforms one quantum object into two entangled objects that remain mysteriously connected across any distance. What happens when you send powerful laser light through a special crystal? Sometimes, the crystal performs a magic trick. One photon goes in, but two entangled photons come out. Scientists call this spontaneous parametric downconversion. The crystal contains atoms arranged in a precise pattern that can split high-energy photons into pairs of lower-energy photons. This process happens randomly and unpredictably. The original photon carries more energy than either of its children. The crystal divides this energy between two new photons that emerge at different angles. These twin photons share the quantum properties of their parent. This splitting preserves all the original photon's quantum characteristics. If the parent had vertical polarization, one child gets vertical and the other gets horizontal. The crystal forces them to share complementary properties. Spontaneous parametric downconversion became the standard method for creating entangled photons in laboratories around the world. Most entanglement experiments rely on a crystal with an almost unpronounceable name, beta barium borate, or BBO for short. This crystal has unique properties that make quantum twin creation possible. BBO crystals are cut and polished to exact specifications. The atoms inside arrange themselves in a pattern that can split photons efficiently. When ultraviolet light hits the crystal, pairs of red photons emerge at precise angles. The crystal acts like a quantum factory. Scientists shine powerful ultraviolet lasers through thin BBO wafers. Out come streams of entangled red photon pairs, each pair sharing perfect quantum correlations. Temperature and alignment must be controlled precisely. Small changes in crystal orientation or temperature can destroy the entanglement creation process. Scientists spend months perfecting the setup. BBO crystals made entanglement experiments practical for the first time. Before these crystals, creating entangled particles required massive, expensive equipment. Measuring photon polarization requires nothing more than a piece of polarizing material. The same technology found in sunglasses can probe the deepest mysteries of quantum mechanics. polarizing filters act like quantum decision makers. When a photon hits the filter, it must choose to either pass through or get blocked. The filter forces photons in superposition to collapse into definite polarization states. Each filter has an orientation: vertical, horizontal, or diagonal. Photons aligned with the filter pass through easily. Photons perpendicular to the filter get blocked completely. Photons at intermediate angles have a chance of getting through. Scientists can rotate these filters to any angle they choose. This allows them to measure photon polarization in any direction. The measurement results reveal the quantum correlations between entangled photon pairs. Polarization measurement became the foundation for most entanglement experiments because it's simple, reliable, and easily controlled. Can you separate particles based on their spin direction? Two German physicists proved this was possible using a cleverly designed magnetic field experiment. Otto Stern and Walther Gerlach created an experimental setup that became legendary. They sent silver atoms through a specially shaped magnetic field. The field was stronger on one side than the other. Classical physics predicted a continuous smear of deflected atoms. But the experiment revealed something shocking instead. The atoms split into exactly two beams, no more, no less. This proved that particle spin can only have discrete values. The atoms were either deflected up or deflected down. There were no intermediate positions. Quantum spin was quantized. The Stern-Gerlach experiment became the standard method for measuring particle spin and proved that quantum mechanics operated in the macroscopic world. Why can't you just measure entangled particles whenever you feel like it? Because proving entanglement requires perfect coordination between measurements at different locations. Scientists must measure both particles in an entangled pair within a tiny time window. If too much time passes between measurements, the correlations become meaningless. The particles might have interacted with their environment and lost their entanglement. This creates an enormous technical challenge. Laboratories might be separated by kilometers. Communication between distant detectors takes time. Coordinating simultaneous measurements requires precise timing equipment. Light travels at a finite speed, even between nearby detectors. Scientists must account for these delays when comparing measurement results. Timing errors can make genuine entanglement look like classical correlation. Simultaneous measurement became one of the hardest requirements to satisfy in entanglement experiments. Perfect particle detectors don't exist. Even the best detectors miss a significant fraction of the particles sent their way. This creates a serious problem for entanglement experiments. Photon detectors typically catch only about half the photons that hit them. The other half vanish without triggering any signal. Scientists call this the detection efficiency problem. Missing particles create holes in the data. If you only detect one photon from an entangled pair, you can't verify the correlation. The experiment becomes biased toward successful detections. Skeptics argued this could explain away entanglement entirely. Maybe the correlations only appeared strong because detectors preferentially caught certain types of photon pairs. Detection efficiency became one of the major loopholes that had to be closed before scientists could claim definitive proof of entanglement. How do you prove two particles detected at different times actually came from the same entangled pair? Scientists developed an ingenious solution. They give each detection event a precise timestamp. Atomic clocks provide timing accuracy down to billionths of a second. When a detector registers a particle, it immediately records the exact time. Scientists can later compare timestamps to identify which detections came from the same original pair. Entangled particles are created simultaneously and travel at known speeds. Scientists can calculate exactly when partner particles should arrive at distant detectors. Only detections with matching timestamps get included in the correlation analysis. This time tagging method allows scientists to work with very weak sources of entangled particles. Even if most particle pairs get lost, the few successful detections can be properly matched. Precise timestamp recording became essential for proving entanglement with realistic, imperfect experimental equipment. Raw experimental data doesn't directly reveal entanglement. Scientists must perform complex calculations to extract the quantum correlations hiding in their measurements. The correlation function compares measurement results from both detectors. It calculates how often both detectors agree versus how often they disagree. Classical physics predicts specific limits on these correlation strengths. Scientists typically need thousands of measurement pairs to calculate reliable correlation functions. Each individual measurement is random, but the statistical pattern reveals the underlying quantum mechanics. The correlation function produces a single number that summarizes the strength of entanglement. Values above certain thresholds prove that quantum mechanics is operating. Values below those thresholds suggest classical physics might explain the results. Correlation function analysis became the standard method for proving that experimental results couldn't be explained by classical physics alone. Creating stable, long-lasting entangled particles requires trapping individual atoms and cooling them to near absolute zero. Scientists use lasers to build invisible prisons that hold atoms perfectly still. Untraps use electric fields to confine charged atoms in small regions of space. The trapped ions float in vacuum, isolated from environmental disturbances. Laser cooling removes almost all their thermal motion. At these ultra-low temperatures, atoms barely move at all. This eliminates most sources of decoherence that would destroy quantum entanglement. The trapped atoms can maintain quantum correlations for minutes or even hours. Scientists can manipulate individual trapped ions with precise laser pulses. They can force atoms into specific quantum states. They can create entanglement between multiple atoms on command. On-trap systems became the gold standard for creating stable, controllable entangled particle systems in laboratory environments. Nuclear magnetic resonance, the same technology used in hospital MRI scanners, can create entangled particles in liquid samples. Scientists discovered this quantum application decades after MRI was developed. NMR works by manipulating atomic nuclei with strong magnetic fields and radio waves. Certain molecules contain nuclei that naturally interact with each other through quantum mechanics. In liquid samples, millions of molecules tumble randomly, but their nuclear spins can become entangled through carefully designed radio wave pulses. Scientists can control entire populations of entangled nuclei simultaneously. Liquid-state MRR doesn't require the extreme conditions needed for other entanglement experiments. Room temperature operation makes these systems easy to build and maintain. NMR entanglement experiments helped prove that quantum effects could survive in warm, noisy environments previously thought impossible for quantum mechanics. Quantum dots are artificial atoms built from semiconductor materials. These tiny structures can generate streams of entangled photons on demand. They represent the future of quantum technology manufacturing. Scientists create quantum dots by growing ultra-thin layers of different semiconductor materials. The layered structure confines electrons to tiny regions smaller than natural atoms. These artificial atoms have precisely controlled properties. When electricity flows through quantum dots, electrons and holes combine to emit photons. The semiconductor structure can be designed to produce entangled photon pairs with specific properties. Quantum dots can be manufactured using the same techniques that create computer chips. This makes them potentially scalable to mass production. Arrays of quantum dots could generate massive amounts of entangled light. Semiconductor quantum dot technology promises to make entangled particles as common and useful as laser light became in the previous century. John Bell discovered a way to test whether Einstein was right about quantum mechanics. He developed a mathematical inequality that must be satisfied if particles carry hidden instructions. Any violation of this inequality would prove quantum mechanics was genuinely strange. Bell's insight was brilliantly simple. If particles have predetermined properties, their correlations must follow certain mathematical limits. These limits apply regardless of what the hidden properties actually are. The inequality works like a cosmic lie detector test. Classical physics with hidden variables can only produce correlations up to a specific strength. Quantum mechanics predicts correlations that exceed these classical limits. Bell created the ultimate experiment to distinguish between Einstein's classical view and quantum weirdness. The mathematical inequality would serve as the referee in this fundamental debate about reality. This mathematical framework transformed philosophical arguments into testable predictions that experiments could definitively resolve. Bell's original inequality was difficult to test experimentally for physicists. Clauser, Horn-Shimony, and Holt developed an improved version that laboratories could actually measure. Scientists call this the CH inequality, named after the four researchers who created it. This version focuses on measuring particle correlations at different angles. It's designed specifically for photon polarization experiments. The CHSH inequality sets a maximum value that classical correlations can reach. No combination of hidden variables can produce correlations stronger than this limit. The mathematics proves this boundary is absolute. Real experiments can measure the quantities in the CH inequality directly. Scientists rotate their polarization filters to specific angles. They count detection events and calculate correlation strengths. The CH inequality became the standard tool for testing quantum mechanics against classical physics in laboratory experiments. Einstein insisted that particles must carry hidden instructions that determine all their properties before measurement. Think of these instructions as invisible programs that tell particles how to behave. These hidden variables would work like secret genetic codes. Each particle would contain complete information about how it should respond to any possible measurement. The randomness in quantum mechanics would just reflect our ignorance of these hidden instructions. A particle's hidden variables might specify spin up when measured vertically, spin down when measured horizontally, spin up when measured diagonally. Every possible measurement angle would have a predetermined answer. This hidden variable theory would restore classical logic to quantum mechanics. Particles would have definite properties whether measured or not. Measurement would simply reveal what was already there. Einstein believed hidden variables would eventually explain all quantum phenomena without requiring impossible instantaneous connections between distant particles. Classical physics operates under a fundamental constraint called locality. Information cannot travel faster than light. One event cannot instantly influence another event at a distant location. Locality means that measuring one particle cannot immediately affect its distant partner. The measurement apparatus can only influence particles in its immediate vicinity. Any correlation between distant measurements must have been established when the particles were created. This creates strict limits on how strongly distant measurements can be correlated. The particles might carry hidden instructions that coordinate their behavior, but these instructions must be programmed in advance when the particles were still together. Bell proved mathematically that locality places absolute bounds on correlation strength. No matter how cleverly the hidden variables are designed, they cannot exceed certain correlation limits. The locality constraint became the foundation for Bell's mathematical proof that classical physics has fundamental limitations. Quantum mechanics makes predictions that violate Bell's inequality. For specific measurement angles, quantum theory predicts correlations stronger than any classical theory can explain. The quantum predictions aren't just slightly above the classical limit. They exceed it by a significant margin that experiments can easily measure. Quantum mechanics doesn't just bend the rules, it breaks them completely. These strong quantum correlations emerge from entanglement itself. The particles don't carry hidden instructions. Instead, they share a single quantum state that transcends space and time. Measurement doesn't reveal predetermined properties, it creates them. The quantum predictions depend on the measurement angles in a very specific way. The correlation strength varies according to the cosine function of the angle between polarization filters. Bell's inequality tests became the ultimate showdown between classical intuition and quantum reality. The strength of quantum correlations depends critically on the angles between measurement devices. Change the angle, and the correlation strength changes in a mathematically precise way. When both polarization filters point in the same direction, entangled photons show perfect correlation. When the filters are perpendicular, the correlation disappears completely. At intermediate angles, the correlation follows a smooth mathematical curve. This angular dependence follows the cosine function exactly. The correlation strength equals the cosine of the angle between the two measurement directions. This creates a characteristic fingerprint that identifies genuine quantum correlations. Classical hidden variable theories cannot reproduce this angular dependence. They can match quantum predictions at some angles, but they fail at others. The cosine function reveals quantum mechanics' unique signature. Scientists use this angular dependence to prove that their experimental results cannot be explained by any classical theory. Proving Bell inequality violation requires massive statistical analysis. Each individual measurement produces a random result. Only the overall pattern reveals whether quantum mechanics or classical physics governs the system. Scientists typically collect thousands of measurement pairs to calculate reliable correlation values. Each measurement is like flipping a quantum coin. The individual result is unpredictable, but the statistics follow precise laws. The experimenters measure particles at several different angle combinations. They calculate correlation strengths for each combination. Then they plug these values into Bell's mathematical formula. If the final calculated value exceeds the classical limit, Bell's inequality is violated. This proves that quantum mechanics operates in the experimental system. Classical physics with hidden variables cannot explain the results. Statistical analysis transforms random quantum events into definitive proof of quantum mechanics' validity. Bell inequality violations prove that particles don't have definite properties before measurement. This destroys the philosophical foundation of classical physics, the belief that objects possess objective properties independent of observation. Scientists call this the collapse of local realism. Realism is the idea that particles have definite properties, whether measured or not. Bell experiments prove realism is false at the quantum level. When Bell's inequality is violated, one of two fundamental assumptions must be abandoned. Either locality is false, or realism is false. Many physicists choose to abandon realism rather than locality. This means quantum particles exist in a state of undefined potential before measurement. Properties don't exist until the moment of observation. Measurement creates reality rather than revealing it. The violation of Bell's inequality marked the end of classical philosophy's dominance in physics. Every successful Bell test proves that quantum correlations are stronger than classical physics allows. The mathematical evidence leaves no room for doubt. Quantum mechanics produces correlations that a simple local hidden variable picture cannot match. The experimental violations consistently exceed classical limits by significant margins. This isn't a subtle effect that requires careful interpretation. The quantum advantage is clear and unmistakable. These results show that entangled particles share genuine non-local correlations. The correlations cannot be explained by hidden variables programmed when the particles were created. They still do not let you send information faster than light. Non-locality becomes an experimentally verified feature of quantum mechanics. The correlations look like they ignore distance, even though they do not behave like a faster-than-light signal. Bell tests transformed quantum non-locality from a philosophical speculation into a proven scientific fact. Bell's theorem created a crisis in physics that continues today. Different interpretations of quantum mechanics offer competing explanations for how Bell inequality violations are possible. The Copenhagen interpretation says measurement creates reality by collapsing the wave function. The many worlds interpretation says all possible measurement outcomes occur simultaneously in parallel universes. Hidden variable theories still exist, but they must abandon locality. Bohm theory proposes non-local hidden variables that coordinate particle behavior through instantaneous correlations. Some interpretations question whether particles have individual existence at all. They suggest that only the quantum system as a whole is real. Individual particles are just manifestations of the underlying unified reality. The interpretation debates rage on because Bell's theorem proves something impossible is happening. But physicists disagree about what that something actually is. Bell's theorem forces us to abandon our most basic assumptions about reality. Either the universe contains correlations that cannot be explained by any local hidden variable story, or objects don't have definite properties until measured. Many physicists accept some form of non-locality rather than give up realism completely. This means the universe allows correlations that do not fit ordinary space-based cause and effect, even while it does not allow faster-than-light messages. This worldview contradicts every human instinct about how reality should work. Objects should be where they are. Events should have local causes. The future should be determined by the present and past. Quantum mechanics demands that we accept a universe where distant events are linked in ways that defy classical intuition, where observation helps define what becomes real, where the classical world emerges from quantum foundations that violate classical logic. Bell's inequality violations prove that the universe is far stranger than human intuition can grasp. Reality operates according to principles that contradict common sense at the deepest level. Two physicists decided to test Bell's inequality in a real laboratory for the first time. Stuart Friedman and John Clauser built an experiment that would either validate quantum mechanics or vindicate Einstein's hidden variable theory. Their 1972 experiment used calcium atoms excited by intense laser light. The excited atoms emitted pairs of entangled photons in opposite directions. Friedman and Clauser measured the photon polarizations and calculated the correlation strengths. The results clearly violated Bell's inequality. The measured correlations exceeded the classical limit by a significant margin. This provided the first experimental evidence that quantum mechanics was genuinely non-local. But skeptics found problems with the experiment. The detection efficiency was too low. Too many photons went undetected. Critics argued this created loopholes that could explain away the Bell violation. Despite these limitations, the Friedman-Clauser experiment marked the beginning of experimental quantum mechanics testing and opened the door to more sophisticated tests. Alain Aspect realized that previous experiments had a fundamental flaw. The measurement settings were chosen before the entangled particles were even created. This gave hidden variables a chance to exploit advanced knowledge of the measurement plan. Aspect's solution was brilliantly simple. He would change the measurement settings while the photons were already flying toward the detectors. This would happen so fast that no signal could coordinate the particles' behavior. His team built ultra-fast optical switches that could redirect photons in just nanoseconds. The switches changed the measurement angles randomly while photons were in flight. Any hidden variable coordination would require faster-than-light communication. The 1982 Aspect experiment still violated Bell's inequality even with rapidly switching measurement settings. This closed what scientists call the locality loophole. No local hidden variable theory could explain the results. Aspect's work convinced most physicists that quantum non-locality was real, but other loopholes remained open for determined skeptics to exploit. Why do so many photons vanish before reaching the detectors? Even the best photon detectors miss a large fraction of the particles sent their way. This creates a serious vulnerability that skeptics exploit to question entanglement experiments. Scientists call this the detection loophole. When detectors have low efficiency, only a subset of particle pairs get successfully measured. Critics argue this subset might be specially selected to show strong correlations. Imagine you're only counting the photon pairs that happen to be detected. What if hidden variables make certain types of pairs easier to detect than others? The measured subset could show artificial correlations that don't represent the full population. Detection efficiencies below a certain threshold allow classical theories to mimic quantum predictions perfectly. The threshold depends on the specific experimental setup, but it's typically around 80% detection efficiency. The detection loophole remained a serious challenge for decades because photon detectors struggled to achieve the required efficiency levels. Can you really choose measurement settings freely, or might the entire universe be conspiring to fool you? This bizarre question strikes at the heart of Bell inequality tests. The freedom of choice loophole suggests that measurement settings might be predetermined by the same hidden variables that control particle behavior. If past events determine both the particle's properties and the experimenter's choices, Bell tests become meaningless. This creates a paranoid scenario where the universe itself conspires to hide the truth. Ancient events might program both particle behavior and human decisions to create fake quantum correlations. Most physicists consider this possibility too absurd to worry about, but determined skeptics can use it to explain away any Bell violation. If choice isn't free, then Bell's inequality doesn't actually test local realism. Scientists address this loophole by using random number generators to choose measurement settings, making human bias irrelevant to the experimental design. By 2015, scientists were tired of skeptics finding new ways to doubt quantum mechanics. Multiple research groups launched a coordinated assault on every remaining loophole simultaneously. These loophole-free experiments combine decades of technological advances. Ultra-efficient detectors captured nearly every photon. Lightning-fast switches changed settings while particles were in flight. Quantum random number generators chose measurement angles. The experiment separated detectors by large distances to prevent any communication between measurement sites. They synchronized timing with atomic clocks. They collected massive statistical samples to eliminate any doubt about the results. Every loophole-free experiment confirmed the same result. Bell's inequality was violated by large margins. No classical theory could explain the correlations. Quantum mechanics passed its ultimate test. The 2015 experiments finally provided definitive proof that Einstein was wrong about hidden variables and that quantum non-locality is an established scientific fact. Does quantum weirdness only apply to massless photons? Scientists needed to prove that entanglement works with particles that have mass. This required completely different experimental techniques. Marcus Espelmier's team created entangled pairs using massive particles instead of photons. They used sophisticated magnetic fields and laser cooling to control particle motion. The technical challenges far exceeded anything required for photon experiments. The massive particle experiments still violated Bell's inequality. Quantum non-locality operates regardless of particle mass. The strange quantum correlations aren't limited to exotic massless particles. This proved that quantum mechanics governs all particles equally. Mass doesn't provide an escape route from quantum weirdness. Every type of particle follows the same bizarre quantum rules. Massive particle entanglement opened new possibilities for quantum technologies that require particles with mass rather than photons. What happens to entangled particles separated by hundreds of miles in space? Chinese scientists launched the world's first quantum satellite to find out. The satellite would test whether quantum correlations survive in the harsh environment of space. The Messias satellite carried sophisticated quantum communication equipment into orbit. It could create entangled photon pairs and beam them down to ground stations separated by vast distances. The experiment tested entanglement over longer distances than ever before. Space-based tests eliminated many terrestrial sources of interference. No atmospheric disturbance, no electromagnetic noise from cities, no vibrations from human activity. The vacuum of space provided an ideal laboratory for quantum experiments. The satellite experiments confirmed that entanglement works perfectly over intercontinental distances. Quantum correlations survive transmission through space without any degradation. Space-based quantum experiments opened the door to global quantum communication networks that could connect any points on Earth through satellites. The detection loophole finally died when scientists developed superconducting detectors with unprecedented efficiency. These devices could capture more than 99% of incoming photons. Superconducting nanowire single-photon detectors work by exploiting quantum effects in ultra-thin wires cooled to near absolute zero. When a photon hits the wire, it temporarily destroys the superconductivity. This creates an electrical pulse that registers the detection. These detectors are so sensitive they can register individual photons with almost perfect reliability. They operate thousands of times faster than previous detectors while maintaining extremely high efficiency. High-efficiency detection eliminated the last refuge for classical explanations of Bell violations. No subset selection could explain away the correlations when virtually every photon pair gets successfully measured. The detector revolution made it impossible for skeptics to use missing particles as an excuse to doubt quantum mechanics. How do you prove that measurement choices are truly random and not predetermined by hidden conspiracies? Scientists turn to quantum mechanics itself to generate genuinely unpredictable numbers. Quantum random number generators exploit the fundamental randomness built into quantum measurement. They measure quantum systems in superposition states to produce numbers that are provably unpredictable. No classical process can generate the same kind of randomness. These quantum random number generators choose measurement settings in real time during experiments. The choices get made by quantum processes that are genuinely random according to the laws of physics themselves. Using quantum randomness to choose measurement settings makes it impossible for hidden variables to predict what measurements will be performed. The universe cannot conspire against experiments that use its own randomness. Quantum random number generation eliminated the freedom of choice loophole and ensured that Bell tests measure genuine physical correlations. In 2022, the Nobel Committee awarded the Physics Prize to 3 scientists who proved that quantum mechanics describes reality accurately. Alain Aspect, John Clauser, and Anton Zeilinger shared the honor for their groundbreaking entanglement experiments. The Nobel Prize recognized decades of painstaking experimental work that transformed quantum mechanics from a theory into established fact. These scientists closed every loophole that skeptics had used to doubt quantum non-locality. Aspect pioneered the fast-switching techniques that eliminated the locality loophole. Clauser performed the first Bell tests and continued refining experimental methods for decades. Zeilinger developed quantum teleportation and advanced entanglement techniques. Their combined work established quantum mechanics as the most precisely tested theory in all of science. No experiment has ever contradicted quantum mechanical predictions when properly performed. The Nobel Prize marked the final victory of quantum mechanics over classical intuition and validated the strangest theory in the history of physics. Imagine a communication system so secure that the laws of physics prevent anyone from breaking it. Quantum key distribution uses entangled particles to create encryption keys that are impossible to intercept without detection. Traditional encryption relies on mathematical complexity that powerful computers might eventually crack. Quantum encryption relies on fundamental physics that no amount of computing power can overcome. When 2 people want to communicate securely, they first share entangled particles. These particles generate matching random numbers that become their secret encryption key. Any attempt to intercept these particles automatically disturbs their quantum state. The eavesdropper's presence becomes immediately obvious because quantum measurement changes the particles being measured. The legitimate users can detect this interference and know their communication has been compromised. Quantum key distribution transforms the act of eavesdropping from an invisible threat into a detectable physical event that reveals itself through the fundamental laws of quantum mechanics. Can you create an exact duplicate of something you've never seen before? Quantum mechanics says this is fundamentally impossible. The no-cloning theorem proves that unknown quantum states cannot be perfectly copied. This theorem protects quantum information from unauthorized duplication. An eavesdropper cannot intercept a quantum message, make a perfect copy, and forward the original without the sender and receiver noticing. Any attempt to measure and copy an unknown quantum state necessarily disturbs it. The measurement process forces the quantum system to choose definite properties, destroying the original superposition state forever. Classical information can be copied endlessly without degradation. Digital files can be duplicated perfectly millions of times. But quantum information follows different rules that prevent perfect duplication. The no-cloning theorem creates a fundamental asymmetry between legitimate users who prepared the quantum states and eavesdroppers who can only measure them imperfectly. How do you use quantum mechanics to share secret keys? Charles Bennett and Gilles Brasser developed a protocol that uses 4 different quantum states to create unbreakable encryption keys. The BEAT-A4 protocol works by sending photons in 4 possible polarization states. 2 states are vertical and horizontal. 2 states are diagonal at 45-degree angles. These 4 states form 2 complementary sets. The sender randomly chooses which state to send for each photon. The receiver randomly chooses which type of measurement to perform. When their choices are compatible, they get matching results. When incompatible, the results are random. After transmission, sender and receiver publicly compare their measurement choices. They keep only the results where both chose compatible measurements. These matching results become their shared secret key. Any eavesdropper who intercepts photons must guess which measurements to perform, introducing errors that the legitimate users can detect and measure. What happens when your quantum communication channel starts producing too many errors? This could mean an eavesdropper is trying to intercept your messages. Error rate monitoring acts like a quantum burglar alarm. In perfect quantum communication, error rates should be extremely low. Random errors from environmental noise typically affect less than a few % of transmitted particles. Higher error rates suggest deliberate interference. An eavesdropper must measure intercepted particles to gain information about them. These measurements disturb the quantum states and introduce additional errors beyond the natural background level. Legitimate users can calculate exactly how many errors different types of eavesdropping attacks would produce. They compare measured error rates to these theoretical predictions to determine if someone is listening. When error rates exceed safe thresholds, users know their communication is compromised and can abort the key distribution process before any secrets are revealed. Quantum teleportation sounds like science fiction, but it's a real phenomenon that moves quantum states from one location to another without the information traveling through the space between. The process requires 3 quantum particles. 2 particles are entangled and shared between sender and receiver. The 3rd particle carries the unknown quantum state that needs to be teleported. The sender performs a special measurement that entangles the unknown state with their half of the shared entangled pair. This measurement destroys the original unknown state while creating classical information about the measurement result. The sender transmits this classical information to the receiver through ordinary communication channels. The receiver uses this information to perform operations on their entangled particle that recreate the original unknown state. Quantum teleportation enables quantum communication networks by allowing quantum states to be transferred between distant locations using entanglement and classical communication. Even if an eavesdropper intercepts some information, privacy amplification can still extract perfectly secure keys from partially compromised data. This mathematical technique concentrates the remaining privacy into a shorter but completely secure key. Privacy amplification works by applying mathematical functions that compress the raw key material. These functions are designed so that any information an eavesdropper obtained becomes diluted and useless. The technique relies on information theory to prove that even partial knowledge of the input doesn't reveal anything about the output. The mathematical transformation creates provable security from imperfect starting material. Users can calculate exactly how much information an eavesdropper might have obtained from error rate measurements. They then apply enough privacy amplification to eliminate any advantage the eavesdropper gained. Privacy amplification transforms quantum key distribution from a fragile process that fails if anyone tries to eavesdrop into a robust system that maintains security even under attack. What if you don't trust your own quantum communication equipment? Device-independent security protocols can guarantee secure communication even when the devices might be compromised or faulty. Traditional quantum cryptography assumes your equipment works exactly as designed. But what if it doesn't? What if it has hidden backdoors or manufacturing defects that compromise security? Device-independent protocols test the equipment by performing Bell inequality measurements. If the devices violate Bell's inequality by sufficient amounts, they must be generating genuine quantum entanglement regardless of their internal construction. The strength of Bell violation provides a lower bound on the security of keys generated by the devices. Strong violations guarantee strong security without needing to trust the device manufacturers or understand the internal workings. Device-independent quantum cryptography provides security guarantees based purely on observed correlations rather than assumptions about how the equipment operates internally. Individual quantum communication links can be combined into networks that span continents. The quantum internet will connect quantum computers and provide global secure communication using entanglement distribution. Quantum networks require specialized nodes that can store, manipulate, and relay quantum information. These nodes use trapped atoms or other quantum systems that can maintain entanglement for extended periods. Creating entanglement between distant nodes requires either direct transmission of quantum particles or entanglement swapping techniques. Multiple shorter links can be combined to create longer connections. The quantum internet will enable distributed quantum computing where multiple quantum processors work together on the same calculation. It will also provide unhackable communication channels for sensitive information. Prototype quantum networks already connect research institutions in several countries, demonstrating the feasibility of large-scale quantum communication infrastructure. Ground-based quantum communication faces distance limitations due to fiber optic losses and atmospheric interference. Quantum satellites overcome these limitations by distributing entanglement through space. The Chinese MISIUS satellite demonstrated that quantum communication works perfectly through the vacuum of space. Satellites can create entangled photon pairs and beam them to ground stations thousands of miles apart. Space-based quantum communication avoids most sources of interference that plague terrestrial systems. No atmospheric turbulence in space. No electromagnetic noise from cities. No physical access points where cables can be tapped. quantum satellite constellations could provide global quantum communication coverage. Any 2 points on Earth could establish secure quantum communication through satellite relays. Space-based quantum networks represent the future of global secure communication and will make quantum cryptography available worldwide. Classical communication signals can be amplified to overcome transmission losses, but quantum signals cannot be amplified without destroying their quantum properties. This creates fundamental limits on quantum communication distance. Classical amplifiers work by measuring weak signals and generating stronger copies, but measuring quantum signals destroys their quantum superposition states. Perfect quantum amplification is impossible due to the no-cloning theorem. Long-distance quantum communication requires quantum repeaters, devices that can extend communication range without destroying quantum information. These repeaters use entanglement swapping and quantum error correction. Quantum repeaters are much more complex than classical amplifiers. They require quantum memories to store particles, high-efficiency detectors, and sophisticated control systems. Current repeater technology is still experimental. The quantum repeater challenge represents one of the major engineering obstacles to building practical long-distance quantum communication networks. Quantum cryptography has moved from research laboratories into commercial applications. Banks, governments, and corporations are already using quantum key distribution for their most sensitive communications. Commercial quantum cryptography systems are available from multiple manufacturers. These systems provide point-to-point secure communication over fiber optic networks up to hundreds of kilometers long. Financial institutions use quantum cryptography to protect high-value transactions and sensitive trading information. Government agencies use it for classified communications that must remain secure for decades. The technology is still expensive and requires specialized maintenance, but costs are falling as the market grows. Quantum cryptography networks are expanding in Europe, Asia, and North America. Commercial quantum cryptography represents the first practical application of quantum entanglement technology and demonstrates that quantum physics can solve real-world problems. Classical computers solve problems by testing solutions one at a time. Quantum computers can explore many possible solutions in parallel using the power of entangled quantum bits. This creates computational abilities that can seem impossible. Quantum parallelism emerges when multiple qubits become entangled with each other. Each additional qubit doubles the number of possibilities the system can represent at once. 10 entangled qubits can explore over 1,000 possibilities at once. The quantum computer doesn't just run faster than classical computers. It explores fundamentally different computational pathways that classical systems cannot access. Entanglement can create shortcuts through calculation space that bypass classical limitations in certain problems. This parallel processing doesn't require multiple processors or complex hardware. A single quantum system naturally explores all possible computational paths through the mysterious power of quantum superposition. Quantum parallelism transforms computation from a sequential process into a massive parallel exploration of solution space that classical physics cannot match. What if a computer bit could be both 0 and 1 at the same time? This quantum version of classical bits is called a qubit. These quantum information units form the foundation of all quantum computing. Classical bits exist in definite states, either 0 or 1, on or off, true or false. Qubits exist in quantum superposition, holding both values simultaneously until measurement forces them to choose. A single qubit, when measured, contains the same amount of classical information as a regular bit. But two entangled qubits can represent 4 different states simultaneously. 3 qubits represent 8 states. The computational power grows exponentially with each additional qubit. Qubits can be created from any quantum system with 2 distinct energy levels. Trapped atoms, superconducting circuits, and photon polarization all serve as viable qubit platforms. The qubit represents a fundamental reimagining of information itself, where data exists in a realm of quantum potential rather than classical certainty. How do you build logic circuits using quantum bits instead of classical bits? The CNO gate creates controlled interactions between qubits that can generate entanglement and perform quantum calculations. The CNO gate works like a quantum light switch. One qubit acts as the control that determines whether the gate affects a second target qubit. If the control is in the 0 state, nothing happens. If the control is in the 1 state, the target qubit gets flipped. When qubits are in superposition, the CNO gate creates something remarkable. The control qubit can be both 0 and 1 simultaneously. This means the target qubit becomes both unchanged and flipped at the same time. This controlled operation entangles the 2 qubits into a single quantum system. Their states become correlated in ways that classical logic gates cannot achieve. The output depends on both qubits collectively rather than individually. CNO gates can be combined to build complex quantum circuits that manipulate entangled qubit systems and perform calculations impossible for classical computers. Peter Shor discovered a quantum algorithm that can factorize large numbers exponentially faster than any known classical method. This threatens the foundation of modern Internet security. Most Internet encryption relies on the difficulty of factorizing large numbers. Classical computers would need impractically long times to factor the enormous numbers used in current security systems. Shor's algorithm could factor them quickly in principle. The algorithm exploits quantum parallelism to find the hidden patterns in large composite numbers. It uses quantum interference to amplify the correct factors while canceling out incorrect guesses. Shor's algorithm doesn't just work faster than classical factorization. It uses fundamentally different mathematical principles that are only available in quantum systems. The algorithm transforms factorization from an impossibly hard problem into a manageable calculation. This quantum algorithm represents both a tremendous opportunity and a serious threat, promising revolutionary computational power while potentially undermining current cryptographic security. Lovegrover developed a quantum search algorithm that can find specific items in unsorted databases much faster than classical computers. This provides a practical advantage for many real-world computing problems. Classical computers must search unsorted databases by checking each item individually. Finding one specific item among 1 million unsorted entries requires checking 500,000 items on average. Grover's algorithm uses quantum amplitude amplification to boost the probability of finding the correct answer. It doesn't examine each database item separately. Instead, it manipulates the quantum amplitudes of all items simultaneously. The quantum search runs in square root time compared to classical searches. A 1,000,000-item search that classically takes 1,000,000 steps can be completed in just 1,000 quantum steps. Grover's algorithm demonstrates that quantum computers provide genuine, practical advantages for everyday computational tasks beyond specialized mathematical problems. Quantum computers are extremely fragile. Environmental noise destroys quantum information much faster than classical data gets corrupted. Quantum error correction protects quantum calculations by encoding logical qubits across multiple physical qubits. Classical error correction works by making multiple copies of important data. If some copies get corrupted, the correct information can be recovered from the undamaged copies, but quantum information cannot be copied due to the no-cloning theorem. Quantum error correction uses clever encoding schemes that spread quantum information across multiple qubits without actually copying it. The encoded logical qubit inherits protection from the correlation patterns between multiple physical qubits. When errors occur in individual physical qubits, the error correction system can detect and fix them without destroying the encoded logical information. This requires sophisticated quantum operations that can manipulate errors without measuring the protected data. Quantum error correction transforms fragile quantum systems into robust platforms capable of performing long computational tasks despite environmental interference. Every quantum computer faces a relentless enemy that gradually destroys its quantum advantages. Decoherence occurs when quantum systems interact with their environment and lose their delicate quantum properties. Quantum computers require perfect isolation from environmental disturbances. Stray electromagnetic fields, thermal vibrations, and cosmic radiation all contribute to decoherence. These interactions gradually transform quantum superposition states into classical mixtures. Decoherence times vary dramatically between different quantum computing platforms. Some systems maintain quantum coherence for microseconds. Others can preserve quantum states for minutes. Longer coherence times allow more complex calculations. The fight against decoherence drives much of quantum computing engineering. Researchers use ultra-low temperatures, electromagnetic shielding, and vibration isolation to protect quantum systems from environmental interference. Decoherence represents the fundamental challenge of quantum computing, maintaining quantum coherence long enough to complete useful calculations before environmental noise destroys the quantum advantages. Today's quantum computers are noisy, limited, and prone to errors. Scientists call this the NUSQ era, noisy intermediate-scale quantum computing. These imperfect machines are teaching us how to extract value from flawed quantum systems. NESC devices cannot run the error-corrected quantum algorithms that promise exponential speedups. Instead, researchers design shorter algorithms that can complete before decoherence destroys the quantum calculation. These near-term quantum algorithms focus on problems where quantum computers might have practical advantages despite their limitations. Quantum chemistry simulations and optimization problems show promise for in-ASCII applications. NISQ research is developing techniques to work around hardware limitations rather than eliminate them. Variational algorithms adapt to hardware noise. Quantum error mitigation reduces error effects without full error correction. The NISQ era represents quantum computing's adolescence. No longer pure research, but not yet mature technology capable of solving all the problems quantum computers promise to address. Google's quantum computer achieved something classical computers could not match at the time. This quantum supremacy demonstration showed that quantum computers can solve certain problems faster than the best available classical methods. The quantum supremacy experiment used a specialized quantum circuit to sample from a particular probability distribution. The quantum computer completed this task in minutes. Classical computers would need impractically long times with then current techniques. Critics argued that the chosen problem was artificial and had no practical applications, but the demonstration proved a crucial point. quantum computers can access computational capabilities beyond classical reach. Quantum supremacy represents a proof of principle rather than immediate practical application. It demonstrates that quantum computing theory works in practice despite hardware imperfections and environmental challenges. This milestone marked quantum computing's transition from theoretical possibility to experimental reality and validated decades of quantum computing research. Trapped-on quantum computers use individual atoms held by electromagnetic fields as qubits. These systems achieve some of the highest fidelity quantum operations available today. Electric and magnetic fields create invisible cages that can trap individual atoms in precise locations. Laser beams manipulate these trapped atoms with extraordinary precision. Different laser frequencies can flip qubit states, create entanglement, and read out measurement results. Trapped-ion systems naturally provide identical qubits because all atoms of the same element are fundamentally identical. This eliminates manufacturing variations that plague other quantum computing approaches. The trapped atoms are nearly perfectly isolated from environmental disturbances. They can maintain quantum coherence for extended periods compared to other qubit technologies. This enables complex quantum algorithms that require many sequential operations. Trapped-ion quantum computers represent one of the most mature quantum computing technologies available today and demonstrate that large-scale quantum computation is achievable with sufficient engineering effort. Superconducting quantum computers use electrical circuits cooled to near absolute zero to create artificial atoms that serve as qubits. These systems provide the fastest quantum gates available and enable rapid quantum calculations. Superconducting circuits become artificial atoms when cooled to temperatures colder than outer space. At these extreme temperatures, electrical currents flow without resistance and create discrete quantum energy levels similar to natural atoms. These artificial atoms can be manufactured using the same semiconductor fabrication techniques that produce computer chips. This enables precise control over qubit properties and allows multiple qubits to be integrated on single chips. Superconducting qubits operate much faster than trapped-ion systems. Quantum gates can be performed in nanoseconds rather than microseconds. This speed advantage enables complex quantum algorithms despite shorter coherence times. Major technology companies have invested heavily in superconducting quantum computing because the technology offers the most direct path to building large-scale quantum processors using existing manufacturing infrastructure. Topological quantum computers would use exotic quantum states that are naturally protected from environmental interference. These theoretical systems could reduce the need for complex error correction and enable fault-tolerant quantum computation. Topological qubits are based on quantum states that depend only on global properties rather than local details. Small environmental disturbances cannot easily affect these global properties, making the qubits naturally resistant to decoherence. The quantum information would be stored in the geometric relationships between multiple particles rather than the properties of individual particles. This distributed storage provides inherent protection against local sources of error. Topological quantum computing remains largely theoretical because the required exotic quantum states are difficult to create and control. Researchers are exploring various approaches, including superconducting systems and semiconductor structures. If successfully developed, topological quantum computers could revolutionize quantum computing by providing naturally error-resistant qubits that maintain quantum coherence for much longer without active error correction. Two entangled particles create impossible correlations. But what happens when you entangle three or more particles together? These multi-particle quantum systems display even stranger behavior that defies classical physics more dramatically. Scientists call these systems GHZ states, named after the three physicists who first studied them. GHZ stands for Greenberger-Horn-Zeilinger. These multi-particle entangled states create correlations that are impossible to explain using any classical theory. Three-particle entanglement produces correlations stronger than any combination of two-particle pairs could achieve. The particles become so deeply connected that measuring any one of them instantly affects all the others simultaneously. GHZ states violate Bell's inequality by larger margins than two-particle systems. They provide even more definitive proof that quantum mechanics operates through genuine non-local connections. Multi-particle entanglement opens new possibilities for quantum technologies that require coordination between many quantum systems working together. Quantum sensors exploit entangled particles to achieve measurement precision that exceeds what classical physics thought possible. These devices can detect changes so small they approach the fundamental limits set by quantum mechanics itself. Classical sensors face an unavoidable limit called the standard quantum limit. Random quantum fluctuations create noise that prevents arbitrarily precise measurements. No classical technology can overcome this fundamental barrier. Entangled particles can sidestep this limitation through a phenomenon called quantum enhancement. Multiple entangled particles can coordinate their measurements to reduce quantum noise below the standard limit. Quantum sensors can detect gravitational waves, magnetic fields, and atomic forces with unprecedented sensitivity. They operate at the boundary between quantum and classical physics, exploiting quantum effects to measure classical phenomena. These quantum-enhanced sensors are revolutionizing fields from fundamental physics to medical imaging by providing measurement capabilities that classical sensors cannot match. Time measurement reaches its ultimate precision when atomic clocks use entangled atoms instead of individual atoms. These quantum timepieces can measure time intervals more accurately than any classical clock ever could. Traditional atomic clocks work by counting the vibrations of individual atoms. Each atom oscillates at a precise frequency that serves as a natural timekeeper. But individual atoms suffer from quantum uncertainty that limits timing precision. Entangled atomic clocks coordinate multiple atoms to reduce timing uncertainty. The entangled atoms share their timing information quantum mechanically. This collective behavior cancels out individual quantum fluctuations. These ultra-precise atomic clocks can detect time differences caused by gravitational effects. They're sensitive enough to measure how gravity changes time by tiny amounts across different altitudes. Entangled atomic clocks are pushing time measurement precision toward the fundamental limits imposed by quantum mechanics and relativity theory. Gravitational wave detectors use quantum entanglement to sense distortions in space itself. These massive instruments can detect changes in distance smaller than a fraction of a proton diameter. LIGO detectors work by measuring tiny changes in the distance traveled by laser light. When gravitational waves pass through Earth, they stretch and compress space by incredibly small amounts. Quantum entanglement enhances the sensitivity of these measurements. Entangled photons can detect distance changes that would be impossible to measure using classical light sources. The quantum enhancement comes from reducing photon noise through entanglement. Classical laser light has random fluctuations that limit measurement precision. Entangled photons can coordinate to minimize these fluctuations. Quantum-enhanced gravitational wave detection opens new windows into the universe by enabling observation of weaker gravitational waves from more distant cosmic events. Some physics problems are too complex for even the most powerful classical computers to solve. Quantum simulators use entangled particles to model these impossible systems directly. Complex quantum systems with many interacting particles create computational challenges that grow exponentially with system size. Classical computers become overwhelmed when trying to simulate large quantum systems. Quantum simulators use one quantum system to model another quantum system. They create controllable quantum environments where scientists can study complex quantum phenomena directly. These quantum simulators can model exotic phases of matter that don't exist naturally on Earth. They can explore quantum magnetism, superconductivity, and other phenomena under precisely controlled conditions. Quantum simulation represents a new way of doing physics where experiments become computational tools for solving theoretical problems that resist mathematical analysis. What happens when you connect multiple quantum computers using entanglement? Distributed quantum computing creates quantum networks where separate processors share quantum information and coordinate their calculations. Individual quantum computers face practical limitations in the number of qubits they can control effectively. Connecting multiple smaller quantum computers through entanglement can overcome these scaling challenges. Quantum networking allows different quantum processors to work together on the same calculation. They can share quantum states and coordinate their operations through entangled connections. This distributed approach offers advantages beyond simply combining computational power. Different quantum computers can specialize in different types of operations while sharing quantum information seamlessly. Distributed quantum computing represents the future of large-scale quantum computation where networks of quantum processors work together to solve problems beyond the reach of individual machines. Machine learning algorithms can exploit quantum entanglement to process information in fundamentally new ways. Quantum machine learning uses quantum superposition to explore multiple learning strategies simultaneously. Classical machine learning algorithms process information sequentially. They test different patterns and adjust their behavior based on training data. This sequential approach can be slow for complex pattern recognition problems. Quantum machine learning algorithms can explore multiple pattern recognition strategies in parallel through quantum superposition. They can test many different approaches simultaneously and use quantum interference to amplify successful patterns. Entanglement allows different parts of quantum learning algorithms to coordinate their behavior. Multiple quantum processors can share learning information through entangled connections. Quantum machine learning could revolutionize artificial intelligence by providing fundamentally new approaches to pattern recognition and decision-making that classical computers cannot achieve. Why do scientists want to perform quantum experiments in space? Earth's environment creates unavoidable disturbances that interfere with delicate quantum systems. Space provides the ultimate isolation chamber for quantum research. The International Space Station offers a unique laboratory environment completely isolated from terrestrial interference. No ground vibrations, no atmospheric turbulence, no electromagnetic noise from cities. Microgravity eliminates gravitational effects that can disturb quantum experiments on Earth. Entangled particles can maintain their quantum correlations for longer periods in the weightless environment of space. space experiments can test quantum mechanics under conditions impossible to achieve on Earth. They can explore how quantum entanglement behaves over longer distances and longer time periods. These orbital quantum laboratories represent the frontier of quantum research, where the ultimate limits of quantum mechanics can be explored without earthly constraints. Could quantum entanglement play a role in biological processes? Scientists are discovering that quantum effects might be crucial for photosynthesis, bird navigation, and other biological phenomena. Photosynthesis in plants achieves nearly perfect energy efficiency. This efficiency might depend on quantum coherence that allows energy to explore multiple pathways simultaneously through plant molecular structures. Migrating birds can navigate using Earth's magnetic field with extraordinary precision. This navigation ability might rely on quantum entanglement in special molecules in their eyes. Some researchers propose that quantum effects could be involved in neural processing and possibly even consciousness itself. These ideas remain highly speculative and controversial. The study of quantum biology explores whether evolution has learned to exploit quantum mechanical effects for biological advantage in living systems. Quantum entanglement forces us to reconsider fundamental questions about consciousness, free will, and the nature of reality itself. These philosophical implications extend far beyond physics. Does consciousness require quantum mechanics? Some theories suggest that conscious awareness emerges from quantum processes in the brain. These ideas remain unproven, but continue to generate intense debate. Quantum mechanics raises questions about determinism and free will. If the universe operates through genuine quantum randomness, what does this mean for causality and human choice? The measurement problem in quantum mechanics touches on deep questions about the role of observers in creating reality. Does consciousness collapse the wave function? Or does reality exist independently of observation? Quantum entanglement suggests that the universe might be fundamentally interconnected in ways that transcend space and time. This could have profound implications for how we understand our place in the cosmic order. These philosophical questions may never have definitive answers, but quantum entanglement ensures they remain central to our understanding of reality's deepest nature.